Hello, right, so this is the second part of the series of an exploration of important experiments done in photosynthesis, number 2. So right now we're gonna talk about another experiment. As you can see, it's the colorimetric measurement of the quantum requirement of photosynthesis. So that might be a bit confusing to understand, but um, colorimetry, if you're a science student, you should know what this means already. Basically, you're comparing heat energy in order to figure out the uh, total energy that is required for a particular chemical reaction to proceed. And the quantum requirement here is basically the number of photons that is required or that is absorbed for each cycle of photosynthesis. So some guy, he made use of heat energy to determine the exact number of photons that are required for photosynthesis to proceed. And it's a really interesting question because if you think about it, how many photons uh, does it require for each cycle of photosynthesis? Or actually, let's change that question a bit. How many photons does it require for every molecule of oxygen to be released? And you can make a guess in your head. Uh, Try to answer it with your own logic, because I'm gonna give you the answer, like, because it's at the next slide, or not yet actually. But you can continue to think about it. So these series of experiments, so this is just one of the experiments done. Loads of experiments have been done, and that is in part due to a controversy that happened over the different values that the scientists reported. So there are conflicting values, conflicting arguments that are going around, and that happened during the early 20th century to the mid 20th century. So it lasted for a pretty long time. Alright, so here's the big reveal to the answer. Um, it's actually within this range. So if you had like 100 photons or 1,000 photons in mind, it doesn't actually require that many photons to power the process of photosynthesis. It's only within the 2-digit range. But still, there are people who are arguing. On one side, some group of people, Bob Emerson and friends, they had a value of 12 and they thought it was correct. On the other hand, another group of scientists led by Otto Warburg, they said that 4 is the right answer for the amount of photons that are required. So these two have been fighting for over 50 years, and the reason why it lasted that long was because Otto Warburg is a Nobel Prize winning scientist, so he has lots of influence, lots of exposure, lots of fame. So a lot of people, they want to believe him, and he also wants to believe himself because he is a Nobel Prize winner. It would ruin his pride if he didn't. And a lot of people, Bob Emerson especially, had difficulty fighting or presenting conflicting results with Otto Warburg because he is a Nobel Prize winner and he has a high standing. So there will be some damage to reputation. There will be some drama involved. So that's why it took a really long time before the correct answer was finally determined. And the correct answer is by Bob Emerson and friends with a quantum requirement of 12. Well, actually, that ranges from 8 to 12. It doesn't have a specific value, of course. While Otto Warburg's range lies from 3 to 4. So as you can see, it's pretty different. Bob Emerson has like 2 said that it requires 2 to 3 times more. So that's a pretty big difference in mind. But why was Otto wrong? Well, he used theoretical methods and calculations to determine that 4 quanta is... Wait, I should explain what quanta means. I don't think I did that. Quanta is basically the amount of energy that is contained within a particle of a photon. Alright, so when we say 8 to 12 quanta, that means 8 to 12 photons are absorbed, or like 8 to 12 photons worth of energy is being absorbed. That's the more like technical way to put it. So through theoretical methods and calculation, an amount of energy that corresponds to 4 photon particles are required. And that happens through Einstein's theory of photochemical equivalency, which states that for each quanta of radiation that a substance absorbs, one molecule of the substance reacts. So since photons, they cause the excitement of electrons within the chlorophyll when the photons are absorbed, basically Einstein's theory states that one photon excites one electron, so that happens in a 1-to-1 ratio as the theory suggests. So if you look at the bottom here, this is the formula for the splitting of water to generate one oxygen molecule. So you can see that this reaction involves 4 electrons. So by Einstein's law, 4 quanta or 4 photons are absorbed for each O2 that is produced, and that is how you arrive at the theoretical answer of 4 quanta. So what Otto did was he used a circular argument, which is something you really shouldn't do. So he basically began with the assumption. He began with the belief that 4 quanta is the right answer. So when he did the real experiments, the practical experiment to arrive to that answer, whenever he got values of 8 to 12, which like corresponded to what these other guys found, he would change the procedures of the experiment. He would change the temperature, he'd change the light intensity, he'd change the solution, he'd just change everything that he can in order to get the values of 3 to 4 quanta. And it's not something that you're supposed to do, because at that point you're just like purposely changing the experiment in order to get the values that you want, so that you can't report that as true results. But he was held by his ego, he was held by his pride, and he wanted to be correct, and he didn't want to admit defeat. So that's like one of the reasons why this thing lasted for so long. Just because one Nobel Prize winner was stuck up with like the whole controversy of what happened, and he didn't want to ruin his reputation. But why was the theoretical method wrong? I mean, following this logic, it seems pretty logical, and like nothing is wrong with it. I mean, at first glance, but why is it wrong? And the answer is I won't tell you yet. And that's because if you're a biology student, you should have all the necessary information that you need in order to figure out why this line of reasoning, why this logic turns out to be wrong. It's possible to figure out if you're a biology student, if you've studied photosynthesis, then the information is already there and you just have to connect the dots. So you can think about it while I continue. I will reveal the answer at the end though, so don't worry about that. This is the photocolorimetry experiment. So this is one of the methods that was used to determine the answer of 8 to 12. A bunch of other methods are used, but those involve like some weird and fancy maths that I don't want to be involved with. This one involves simple math, as you will see later, so it's should be pretty easy to explain. So now, what the experiment consisted of was two samples. This cup thing here, I can't find like the a proper image for like the exact scientific apparatus that was used, but it looks pretty similar to a silver cup. So that's what we're gonna use as the image instead. The real scientific apparatus doesn't look like this, okay? This is just a random silver cup that is supposed to represent the real scientific apparatus that was used. What does the scientific apparatus do? What does the scientific apparatus do? It measures sensitive heat changes through electricity or something like that. And so it will measure heat emissions from these pieces of leaves that are put inside of it. Now, why is heat involved? Well, it's because photons, they get converted into heat energy. Well, why do you think it gets hot when the sun comes out? Well, that's because as the light rays hit the surface, the photons get absorbed, and most of them turn into heat energy. Of course, some of it gets reflected. That's how you're able to see things, but we're going to work on the general assumption that all of these photons are being converted into heat energy. Now, this first sample here contains a leaf which is able to do photosynthesis, while this second sample here consists of a leaf that cannot do photosynthesis. So if you compare these two leaves together, well, some of the photons, they will definitely get absorbed here, but they'll not turn into heat energy. They will turn into chemical energy for use in photosynthesis. While in the second sample, that doesn't happen at all. So if you think about it, 100% of the photons, if you like shine a light on the leaf, 100% of the photons in this second case will just be converted to heat energy. While if you shine a light onto this leaf here, some of that photon is going to be absorbed and be converted to chemical energy as it is going on in the cycle of photosynthesis. So like we can assume that 100% of the photons are being converted here into heat energy, while about only 70 or 60% of the photons are being converted into heat energy. And that's why in the second case here, the leaf will emit more heat energy than number one, because some of the photons in number one are being used for photosynthesis and not for heat. That's why this leaf will be cooler than this leaf. Alright, so let's move on to the math stuff. It may seem a bit difficult at first, but we're going to go through them one by one, okay? So we have 1 minus HA over HI. HA is the heat released by the active leaf, while HI is the heat released by the inactive leaf. So the active leaf refers to the one that can do photosynthesis, while the inactive leaf is the one that can't do photosynthesis. So 1 minus HA over HI, we can convert that into HI minus HA over HI. And that's because 1 turns into HI over HI, because the same number divided by the same number turns into 1. And you combine the fraction, you get this amount. So HI is basically the heat from the inactive sample. We worked on the general assumption that 100% of the photons are being converted into heat energy. So when we were measuring the heat from the inactive sample, we can directly translate that into the energy that comes from the photons. Well, when we look at the numerator, HI over HA, we're basically taking the difference between these two heat samples of heat. Why is there a difference? Well, that's because some of it is being absorbed for photosynthesis here, while none of it is being absorbed for photosynthesis here. So when you take the difference between 1 and 2, you're going to get the total amount of energy that has been absorbed. So when you're calculating the difference here, HI minus HA, there's a difference there because HA is less than HI because like photosynthesis happens and it takes in some of that energy. So when you're calculating the difference, it refers to the energy absorbed by the process of photosynthesis. Alright, so I hope that first equation is clear. Now we're going to move on to the bottom one here. Phi is equal to mole of O2 released over mole of photons. So when we say that phi is 0.1, for example, we're saying that it's basically the ratio is 1 over 10, right? Because 1 divided by 10 is 0.1. So we're saying that 1 oxygen is released for every 10 photons. So it refers to the ratio between that value. And this is what we're hoping to calculate because it will give us the answer to the quantum requirement, which I showed in the first slide. Now consider multiplying phi with delta E divided by NHV. What is delta E? Delta E, so like this thing is directly copied from here. So as you can see my mouse there, yeah. So delta E refers to this sentence over here, energy absorbed per mole of product. Alright, so delta E, if you're like a chemistry student, you know like that every reaction, like it's either endothermic or exothermic, and that will have a certain like energy value to it. So sometimes like this reaction, it's like 20 kilojoules per mole or it's like 10 kilojoules per mole. So that's the value of delta E in this case. So it's the amount of energy absorbed, and that's because photosynthesis is an endothermic process. So it absorbs energy. So it refers to the energy absorbed per mole of product. Product in this case, we're going to be using O2 as a reference point. So it's the amount of energy that is absorbed for each oxygen that is generated by photosynthesis, and that is easy to calculate through a different experiment, or you can calculate it also through theoretical methods like the bond enthalpy. So like you like count the number of bonds, and then each bond has a specific energy value, and you use that to determine the delta E. Now if you look at the bottom, NHV, it stands for, well, the N is the Avogadro's number, H is Planck's constant, and V is the frequency of the photon. So photons come in different frequency, or a better way to say it is like photons come in different wavelengths of light. So you have red photons, blue photons, each corresponding to a different color of light. And it depends on like the specific bulb that you're using for the experiment. If you calculate all these numbers, you'll get the energy per mole of photon. And again, if you're a physics student, you can probably understand it better, but I haven't dabbled with it much. So like it took me a lot of time to understand this, but I eventually did, so yay. So when you multiply all of these together, so mole of photons multiplied by energy per mole of photons, you're going to get total energy from photons, right? That's pretty logical to convert like what's going on at the bottom into this thing here. And what's at the top, mole of O2 released multiplied by energy absorbed per oxygen that is generated as a product. So what you get in total is total energy absorbed, right? So pretty easy to figure out why that's so. If you compare this equation with this equation, you'll notice that they're exactly the same. So you can equalize, I think that's a word. You can equalize them together. So 1 minus HA over HI is equal to phi multiplied by delta E over NHV. Again, HA and HI is a value that you have calculated already through this experiment here. Yeah, I just showed like a single frame there. I didn't mean to like switch back so quickly, but you get the idea. So you did the experiment already with the leaf, and you have the values here. You also have the value of delta E. Like I said, you can figure that out from a different experiment, or you can theoretically calculate it. NHV is something that is already determined. Avogadro's number, Planck's constant, the frequency of the photon, all of that stuff you already have already. So mathematically it is possible to calculate phi, and that is what he did. By he I'm referring to Arnold. Yeah, I forgot what the W stands for. But yeah, so this experiment was done in 1949. And he got values of 9, 11, 10, and 15 for all these different species of plants. I think chlorella is an algae. Yeah, it's used a lot in photosynthesis research as a sample species, sample organism. I don't know. So basically, he got a value of 9. And that means that 9 photons are absorbed for each oxygen that is generated. And you also have values of 11, 10, and 15. All of those are similar to the range of 8 to 12 as was determined by other scientists at the time. But this is, once again, like I said, a very easy way to calculate it. Like other people, they use like much different methods that are too complicated for me to understand. But this is simple enough, okay? Right now I'm about to show you the answer on the next slide of why the theoretical answer was wrong from earlier before. I'm gonna go back. Yeah, why was Otto wrong? So if you figured it out, congratulations. Right. So why was the theoretical value incorrect? Well, that's because, remember, there's two photosystems at that time in the early 1900s. They had no idea that there were two photosystems. They thought that there was only one. So when they're doing all the theoretical logic behind that, they said like, oh, H2O, it splits up the hydrogen, gets attached to a carrier molecule. We already discussed the carrier molecule before in the previous video, and that carrier molecule carries the hydrogen, which gets excited by HV. So HV is basically the photon. It comes from this equation here, the HV there. So just refer to HV as a single photon. So for hydrogen, it gets excited by 4 photons, and it gets sent to a higher state of energy, and that is illustrated here by the shift from H being to Z to being connected with Y. So it's attached to a carrier molecule with higher energy. And they thought that that was it, right? They thought that HY, after HY was generated, it directly went over here to the Calvin cycle. But that's not what really happened, because remember, photosynthesis, there's two photosystems. So the photons get absorbed in photosystem 2, which is over here, and it gets absorbed again in photosystem 1. So the same process repeats. So you have 4 electrons here that are being energized, and the same process happens again as it switched carriers again within the first photosystem. So they didn't know that it happened twice, which was why the theoretical calculations were incorrect. Einstein's theory is still correct, though. He wasn't wrong. Four photons for 4 hydrogen. Same thing here, 4 photons for 4 hydrogen. Einstein's theory is still correct. It's just that they applied it incorrectly because they didn't have the knowledge of the existence of another photosystem. So that's why there was an argument or a controversy between the different values 4 versus 8. Does it happen once or does it happen twice? And eventually, like this 8, the value of 8 there, it was used to like develop theories to show that there were 2 different photosystems. So yeah, really cool. And we'll talk about the different photosystems in, I think, like the last part of this series of videos. And yeah, that's it.